Thermochemistry. This is the answers video for day 66, Hess's Law. It was originally scheduled to be due on Monday, May the 9th, but since I'm just getting this answers video up later than that, it will be due on Friday, May the 13th. This will not be on the test that's coming up on May the 17th. This will not be on that. Thermochemistry will not be a part of that test. Okay, so let's go ahead and get started. So what does thermochemistry study, and why is heat energy important in chemical reactions? Okay, so I'm not going to write that out. I'm going to say it. It's in the video. But let me just say what that is. Thermochemistry studies heat going into or coming out of a chemical reaction. The reason it's important in chemistry is because heat energy is the only type of energy that enters or that either goes into or comes out of a chemical reaction, which means that any energy that's used in creating chemical bonds or being released by chemical bonds goes in and comes out in the form of heat energy. So if we can study the amount of heat going into or coming out of a chemical reaction, we know how much energy is in the chemical bonds. For example, when gasoline is manufactured to power cars, chemists want to know how much energy is in that gasoline, is in the bonds of that gasoline, because that goes into actually not heat, not just heat, but it goes into making the car move. So they want to know how much energy is in chemical bonds. There's just a million reasons why chemists want to know how much energy is in chemical bonds. And so by studying the heat going into or out of a chemical reaction, they can determine how much energy is in the chemical bonds. Okay, question 2 is there's a Hess's Law problem in the video for day 66, so watch that, copy that. It's a little bit of writing, but go ahead and copy that, learn how that problem is worked, and that's your sample problem. Now I'm going to go through and work all the problems here, so I'll move on over to page 2. Okay, so I'm assuming that you watched the video and you understand the concepts that were done in that problem that you did on the front page and that was done in the video. So use Hess's Law to compute the enthalpy of reaction or enthalpy of combustion for the following. So what you're trying to do is create this reaction out of these two reactions. And the reason you want to do that is you know the enthalpies of reaction of this reaction and this one. So if you can recreate this reaction out of these two and then add up the enthalpies of reaction here, you'll know what the unknown enthalpy of reaction. This is really what we're trying to know, is what's the unknown delta H of this reaction. Okay, so we get it from these two after we've made these two reactions look like this one up here, okay? So the strategy, there's 3 things you can do. You can reverse the reaction. That will change the sign on the enthalpy. You can multiply through by a number. That will multiply the enthalpy by that same number. And at the end, what you can do to finally create the target reaction is you can add these two reactions together. Things on opposite sides of the arrow cancel out, or subtract rather from each other. Things on the same side add to each other, okay? So let's go ahead and do this. So I'm going to first label the reactions. This is a reaction number 1. This is reaction number 2. Okay, so what you want to do is find something that's in the target that you only see one time down here among these two. Okay, so what is something that would meet that requirement? Well, CO is in the target reaction, and I see CO one time down here. It's the only place I see it, so I'm going to look at that. And by the way, these, in parentheses, the letters are the states, either solid or gas, could be liquid, but in this problem set, it's going to be solid or gas. So you can ignore writing those. That's just excess writing that you don't need to do. Okay, so you can skip writing those. Okay, so I see CO there's 1 mole of it. If you don't have a number or coefficient, it means it's 1. And it's on the right side of the arrow. If I look down here, this CO also has a coefficient of 1 because I don't see anything there. But it's on the left side of the arrow. So what I'm going to need to do is reverse equation 2. I'm going to need to turn it around so that the CO comes over to the right side of the arrow. So I'm going to come down here and I'm going to write 1A and 2A. They simply correspond to these two equations after I've made some change, or maybe even not even have made a change. Okay, so what I'm looking at here is reaction 2 to deal with the CO. So I'm going to bring it down here and I'm going to turn it around. So CO2 comes over here This CO2 comes over on the right side or on the left side of the arrow, and then everything else, I can go ahead and draw the arrow. These two things come over on the right side. Okay, and by flipping that, I've changed this number to a positive 283. All right, so that takes care of that. Once you've used a reaction or done something to it, sometimes you need to do two things to it, but I know I'm not going to have to here, because if I do anything else to this reaction, I'm going to change this CO into something else, maybe 2CO or something. I don't want to do anything else to this reaction. So I'm going to go ahead and put a line through it lightly like that, so I don't make a mistake of adding that number in at the end. Okay, now what else do we see? We see that we have a C on the left of equation 1. It's on the left side of the arrow, and there's 1 mole because you don't see a number there. And up here in the target, it's also on the left side, and it's 1 mole. That means I have exactly what I need for C, so I don't want to change equation 1. But I'm still going to rewrite it down below, because I want to get to where I go from these two equations to two equations. You want to move them together. So I'm going to go ahead and write this anyway. That means I didn't change the enthalpy. Okay, so I've done something with both reactions. I've done with this one. All right, so now I'm ready for the third part of Hess's law, which is you can add and subtract. So I'm going to draw a line down here. I want to come up with my final reaction. So I have CO2 on the left of 2A and on the right of 1A. Since they're on opposite sides, they're going to subtract. So CO2 minus CO2, basically, they cancel out. Okay. The C here. I don't see it anywhere else down here, so that means it's going to come down and be part of my final reaction. Okay, the CO I don't see anywhere else, so that means it's going to come down. It's on the right side of the arrow, so I'm going to draw the arrow right here, and I'm going to write the CO way over here, because I don't know what else I'm going to want to write down here, so I just leave a lot of space. So the CO comes down here. Okay, I'm going to go ahead and put a box around those, indicating that I used them. I didn't cancel them out, the CO. So the only thing I have left is an O2 on the left side of this arrow and a 1/2 O2 on the right side of the equation 2A arrow. So that means they're going to subtract since they're on opposite sides. So 1 O2 minus 1/2 O2, just think of what's 1 minus 1/2. It equals 1/2. And it's going to end up over here because this is the bigger of the two numbers. This is a 1 O2. And this is 1/2 O2, so 1 minus 1/2 is going to put a 1/2 over on the left side of the arrow. So plus 1/2 O2. Okay, and I look at this reaction down here, and it's exactly the same as the target. So I made this reaction match up with the target. So now what you do is you add these two together. The only thing I needed to do was change the sign on equation 2A earlier. So now you get out a calculator and you add those two together. And that gives us a delta H equal to negative 110.5 kilojoules. Okay, and that delta, it should be delta H equals, that's delta H. Let me write that properly. Delta H equals that. So that's the number up here, equals negative 110.5 kilojoules. And that's your final answer. That's the enthalpy that will take place. That much heat will come out of this reaction when it's combusted, or when it's produced, actually. Okay. So this next one, number 4, is the most challenging one. It has 3 equations that you have to use to create this down here. So let's go ahead and get started. We're going to label them. Always label your equations so you don't get lost, and we're trying to recreate this target down here. Okay, so I want to find something in the target that appears only once up here. All right, and let's see what we got. We got N2O, and I see that, I only see that right here. So I'm going to use N2O. All right, so I need to have one N2O because there's no coefficient. Here I have 2 N2O. All right, now they're both on the left side of the arrow, so that means I don't need to reverse the equation 3. It's good the way it is, but I need only 1/2 of that value to get 1 N2O. So I'm going to multiply equation 3 by 1/2. So I'll put that over here, 1/2 times this equation. So I'm going to come down here and I'm going to write equation 1A, 2A, 3A, and this is equation 3, so it's coming down here. So it's 1/2 times 2 is N2O. And that's what I need. I need 1 N2O right there. Okay, 1/2 times 2N2 is going to be just N2. 1/2 times 2 is 1, so it's 1 N2. I'm not going to write the 1. And 1/2 times O2 is 1/2 O2. And then the delta H, which is negative 163.2, is going to also be multiplied by 1/2. And that gives us negative 81.6 kilojoules. Okay, so I've taken care of equation 3. I'm going to lightly draw a line through it. I don't want to use it again. All right, now I'm going to come down here and find something else. I have NO2 here, and if I look up here, NO2 is there and nowhere else. So NO2 is only right there in equation 2. So two things need to happen here. First of all, it has to be on the left side because the NO2 in the target is on the left side of the arrow. So this NO2 has to come over to the left side. The other thing is there's 2 NO2 and we only want 1 NO2. So we're going to have to do two things to this. We're going to have to reverse and multiply by 1/2. So I'm going to write that up here. Reverse, I'll just abbreviate that REV, and then I'm going to put 1/2 times. So reverse and 1/2 times. Okay, so I'm going to do those all in one step. It's going to be 2A. Okay, so that's going to be 1/2 times 2 is just going to be 1 NO2, and it's going to come over to the left side. So it's NO2. Now here's the arrow is going to go in. Now everything on this side is going to go over to the other side. And this 2NO, again, it's going to move over to the right side and it's going to be multiplied by 1/2. So that's going to give you just NO plus. And then you have O2. It's going to come over to the right side right there. And it's going to be 1/2 O2. Everything got multiplied by 1/2. Okay, so what happened to the coefficient? Well, the sign changed because you reversed the reaction. That changes the sign to a positive 113.1, and then you cut that in half. So we're going to go ahead and do that. Okay, and so that gives us a delta H. So you change it to a positive 113 and divide it by 2. That gives us a delta H of 56.6. Okay, good. So that takes care of that. Now we're going to look at this reaction up here. Or actually, what else do we have down here? We have NO. All right. And let's see what else we have. Well, we have N2 here, but there's no N2 in our final reaction, but we have N2 down here now. So we have one on the right and one on the left. They're going to perfectly cancel out. What about N2NO? We've got 2NO on the right, and down here we have 1NO on the right, and that's going to give us 3NO. So what we're going to do here is we see that reaction 1 shouldn't change at all. It'll work out perfectly if it doesn't change. That might not be quite as obvious, and let me say why. I have N2 on the left here, N2 on the right down here, because we're done with these two reactions. Let me scratch that one out. So that means they're going to cancel out, and they need to because we don't have any N2s in the final reaction. We have 2NO on the right here, and we have NO on the right here in equation 2A. That adds to 3NO on the right, and that's what we have. So if we don't change anything about this reaction, it's going to work out perfectly. So we're going to just copy it down. You still copy it down here even though you're not changing it. So N2 plus O2 produces 2NO. And since we didn't change anything, we don't change the enthalpy. .7, okay? And so now we're ready to add and subtract. So we put a line underneath. Okay, so as I just said a minute ago, N2 on the left of this and N2 on the right of this cancel out. They subtract each other. They're gone. Okay, what else do we have? We have O2, NO, NO, NO. We have N2O here. Okay, so nothing else is going to cancel out. We're going to just add. So here we go. We have N2O here. We don't see it anywhere else, and it's on the left side of the arrow, so we're going to put it here. And what I would just do is draw your arrow right in the center. You don't know how many things are going to go on this side and how many on this side, so just go ahead and draw the arrow right in the middle. It's pretty funny looking arrow, but there it is. That's better. Okay, now NO2. It doesn't appear anywhere else down here, and it's on the left side of the arrow, so plus NO2. By the way, I'm going to put a box around each of those because I actually used them already. Okay. Now, we have 2 NO on the right side of this arrow and 1 NO on the right side of this arrow. So 2 plus 1 equals 3. So on the right side of the arrow, we have 3 NO. Okay, and now the O's are a little bit complicated. Let me go ahead and box these because we used both of them. We added them together to get 3NO. Okay, so on the right side of these two arrows down here, 2 and 3, you have 1/2 O2 plus 1/2 O2. That equals 1 O2. That's on the right side. Over on the left side of this arrow, you also have 1 O2. So this 1 O2 and these two added together making 1 O2 cancel each other out. So again, let me say that again. You added them together first, because they're both on the same side. That gives you 1 O2. Then you have a 1 O2 on the left side over here. So the 1 O2 here and the 1 O2 over here cancel each other out. So I can scratch those out, leave those. There's the final equation, and it matches the target equation right there. It looks exactly like the target. So now what we do is we add these things up. Okay? So it's going to be 180.7 plus 56.6 minus 81.6, and that gives us 155.7. So delta H equals positive 155.7. That means it's an endothermic reaction. Heat's going to be going into it. Okay, and that's your final answer for this reaction right here. Okay, so I don't want any one video to go over 20 minutes, so I'm going to break. This will be part 1 of the answers video. I'll continue the rest of the problems on part 2.